Earth's moving surface is secretly controlling our climate. What if I told you that Earth's climate isn't controlled only by the atmosphere, not only by volcanoes, not even only by carbon dioxide? What if the real puppet master is something far more ancient? The slow, relentless movement of tectonic plates beneath our feet. Today, we're diving into groundbreaking new research that reveals how Earth's shifting surface has shaped global climate for more than 540 million years, driving massive ice ages, extreme greenhouse worlds, and everything in between. This discovery completely changes how scientists understand the planet's carbon cycle, and it may help us better predict Earth's future. Let's begin. Earth has never been a stable planet. Throughout deep time, our world has swung between two dramatic states. On one side, Icehouse periods, when glaciers covered continents, sea levels dropped, and temperatures plunged. On the other, greenhouse periods, when tropical conditions reached the poles and dinosaurs roamed warm, humid landscapes. These shifts weren't small. They transformed ecosystems, reshaped continents, and triggered mass extinctions. For decades, scientists believed these climate changes were driven mainly by fluctuations in atmospheric carbon dioxide, released by volcanoes and absorbed by oceans and forests. But that explanation was incomplete. Something deeper was at work. Traditionally, scientists focused on volcanic arcs. These are chains of volcanoes formed where tectonic plates collide, like the Pacific Ring of Fire. When one plate slides beneath another, rocks melt deep underground, releasing carbon dioxide trapped for millions of years. This carbon dioxide rises through volcanoes and enters the atmosphere. For a long time, volcanic arcs were considered the main source of Earth's natural carbon emissions. But new research tells a very different story. Here's where things get fascinating. Earth's oceans act like giant carbon sponges. They absorb enormous amounts of carbon dioxide from the atmosphere. Over thousands of years, this carbon becomes locked into sediments on the seafloor, forming thick layers of carbon-rich rock, sometimes hundreds of meters deep. Now imagine this. Those sediments don't stay in one place. Tectonic plates slowly drag them across the planet. Eventually, many of these carbon-loaded rocks reach subduction zones, where one plate sinks beneath another. As they descend, heat and pressure release the stored carbon back into Earth's interior, and later back into the atmosphere. This massive recycling system is called the deep carbon cycle, and it operates on timescales of millions of years. Scientists used advanced computer models to reconstruct how tectonic plates moved over the last 540 million years. They tracked where carbon-rich sediments formed, how plates carried them, and where they were eventually recycled. The results were honestly stunning. Their models successfully predicted Earth's major climate shifts. During greenhouse periods, more carbon was released than stored. During icehouse periods, oceans trapped more carbon, lowering atmospheric carbon dioxide and cooling the planet. But here's the shock. For most of Earth's history, the dominant source of atmospheric carbon was not volcanic arcs. It was mid-ocean ridges and continental rifts, places where tectonic plates pull apart and magma rises from below. These regions quietly pumped massive amounts of carbon dioxide into the atmosphere over geological time. Volcanic arcs only became dominant about 120 million years ago. Why? Because of microscopic ocean organisms called planktic calcifiers. These tiny creatures evolved the ability to convert dissolved carbon into calcite shells. When they died, their shells sank to the seafloor, creating enormous carbon-rich sediment deposits. Over time, tectonic plates carried these sediments into subduction zones, increasing carbon release through volcanic arcs. In other words, life itself reshaped Earth's carbon cycle. Small organisms helped rewrite planetary climate. This discovery changes how we understand climate. Earth's temperature isn't controlled by the atmosphere alone. It's regulated by a complex system connecting oceans, tectonic plates, deep-sea sediments, volcanoes, and Earth's molten interior, And while Earth naturally balances carbon over millions of years, humans are adding greenhouse gases in just decades. By studying deep-time climate systems, scientists can build better models, helping us predict future changes and understand the limits of Earth's natural buffering mechanisms. So the next time you stand on solid ground, remember, that ground is moving. It's carrying carbon, it's reshaping oceans, and it's quietly steering Earth's climate. Our planet is not static. It's alive, driven by forces deep beneath our feet. And understanding those forces may be one of the most important discoveries of our time.